Now let's move on and look at measures of variability. Those include the range, the sum of squares, the variance, and the standard deviation. Variability overall wants to look at how much spread is there or dispersion in the scores in a data set, whereas central tendency told us about, again, how to sort of summarize or look at the middle or average central tendency of those scores. Variability is looking at how spread out they are. Okay? Now when we're looking at variability, let's look again at this example set of scores that we have here. It's going to be a little bit easier to see how spread out they are if we arrange the scores from highest to lowest. So let's just start out by rearranging those in that manner. Okay? Exact same scores, just ordered accordingly. Well, now we can start to talk about how spread out the scores are. Now the most intuitive measure of variability is just to say, well, what is the difference between the lowest score and the highest score? Okay? And again, different ways to conceptualize variability are looking at this spread in an individual set of scores. If you think about it in terms of a distribution, again, what you're looking at is how narrow or wide is the distribution. Okay, what we want are measures that are going to tell us if we have a wider distribution, we have greater variability, and a narrow distribution will give us less variability. Well, again, the easiest way to show that is to just look at the total spread in the set of scores, that is the distance or difference between the last and the first score. In this case, looking at the data set that we had earlier, if we take 16 minus 3, that would give us a range of 13. That tells us how many different values are encompassed in this set of scores that we have. Again, that's the most intuitive and basic measure of variability that we have, the range. Now, one problem with the range is it's a single number and it includes only the very first 3 and the very last 16 scores in our data set. Now what we really want to do is to not just say, well, what are these first and last scores? Because think about it, regardless of what those middle scores are, as long as that first and last score are the same, we're going to have a range of 13. So what if our data set was 3, 3, 3, 3, 3, 3, 3, 16? Now we're still going to have a range of 13 because the difference between the first and last score is 13. But in this second situation, the scores obviously aren't spread out nearly as much as they are here. Most of the scores are 3. One score is a little bit different. And so the range is going to be the same. However, the inherent variability that we might think we would see is going to be very different. Now, what this illustrates is a problem where when we're measuring variability, it's going to be much better if we can think of measures that somehow take all of the different scores into account. And what we're going to see is the remaining measures of variability that we're going to look at do exactly that, and they do so with the following concept in mind. When you look at this set of scores, you think about what the middle is. As we saw in the previous part to this lecture, the mean as a measure of central tendency for these scores was 7. Okay, so that's what we know. Well, if we want to think about it, okay, then one of the best measures of variability we can come up with when we talk about how spread out are the scores, what we really mean are how spread out are they from this middle or this center. Okay? In particular then, you can think about conceptually what we're looking for is, on average, how far is each score away from this middle of the distribution, its center, in this case the mean. Again, conceptually what we're looking at here for these remaining measures of variability is conceptually, on average, how far are these scores away from the middle of the distribution. Because if you think about it, if they're further and further away, on average, that's going to lead to greater variability. And intuitively, that's exactly what we're looking for. That's what we mean with variability. There's greater dispersion or spread in the scores. Okay? So let's now just try and figure out a formula to measure exactly what we just said. On average, how far away is each score from the mean? Well, let's do that. Let's look at how far away this first score is from the mean. Well, it's a score of 3. The mean is 7. So the distance or difference between that first score and the mean is 3 minus 7. In other words, 4 units or 4 points. And then let's look at how far away that second score is. It's a score of 4 compared to a score of 7. So if we take 4 minus 7, this one is 3 points away. Well, the next 4 is also 3 points away. And the next one, if we look at the next score, 8 minus 7, and so forth and so on. So what we're looking at is again just taking the distance or difference between each score and the mean to figure out how far away is each score from the mean. Well, then what we want to do is, as we said, we want to find on average how far are these scores away from the mean. So let's just take the average of all of these distances or differences. In other words, let's add up all of these differences. The difference of 3 minus 7, or 4 points, 4 minus 7, 3 points, another 4 minus 7, or 3 points, another 3 points, another 1 point, so forth and so on. Okay? And we're going to look at all of these, add them up, and divide by the number of scores, because we know that's how we take an average. We take whatever the values we're looking at, we add them up, and divide by n the number of values. In this case, we're looking at these differences. So, this is what we've done now, is to put into a formula exactly what we were looking for. On average, how far away is each score from the mean? But there's a problem if we do this. Can anybody anticipate what the problem is going to be if we calculate the sum and then do the division that I'm showing on the screen now? What value is this going to give you? And if you want, take a minute to actually calculate it and see what value you get. You probably, if you did it right, got a value of 0. In fact, every time you do this calculation, every time you add up the difference between each score and the mean, and then take the average of those differences, you're always going to get a value of 0. In fact, that's a specific property of the mean in terms of how you're calculating it. Well, this is going to be a problem for us, because what that's going to tell us, if this is a measure of variability, is every single data set we have is going to have a variability of 0, and that's obviously not the case. Well, what is it that's going on here? In fact, what's going on is these scores that are below the mean, 3 and 4, those values, when you look at those differences, the 3 minus 7 is actually producing a difference of negative 4. 4 minus 7 is producing a difference of negative 3, and so forth and so on. The ones above the mean are producing positive values. 8 minus 7 is producing a positive 1, 9 minus 7 a positive 2, and 16 minus 7 a positive 9. Well, all of those positive values for the mean are always going to exactly cancel out the negative values, and that's always going to produce this value of 0. Okay? So what we're looking at is, even though we're looking at the distance, how many points away from the mean these things are, by the way that we're calculating this, it's making some of those negative, some of them positive, and those negatives and positives are canceling each other out. So what we need to do is to think of a way around that. Well, there's a number of different ways to get around that, keeping this same basic point. So taking this distance of x minus x bar, the distance between an individual score and the mean of the data set from which it comes, we can think of a number of different mathematical devices to make sure that those negative values and those positive values don't cancel out. One simple way to do that is just to take the absolute value, and that is a perfectly valid measure. Okay? And a lot of times you'll even hear about this, calculating a sum of absolute deviations, for example. Now, what we're actually going to do is look at a different method, okay, and one that's used more commonly in statistics for a number of reasons that we're not going to go into detail here. But instead of taking the absolute value, another way to make sure that all of those negative values don't cancel out the positive values is to square them all, and that's exactly what we're going to do. Because as we know, when you take any negative number and square it, it becomes a positive value. So now, regardless of whether an x value is above or below the mean, when you square it, it's going to end up giving you the same value, regardless of, again, whether it is above or below. So, a number that is 2 points above the mean, let's say a value of 9, when you square it is going to give you a value of 4. If we had a score that was 2 points below the mean, which would be 5, that would be negative 2 when we look at x minus x bar, and if we're to square that, it would also be 4. So again, regardless of whether the value is 2 points above or 2 points below the mean, when we square that value, it's going to consistently give us a value of squared difference of 4. Then what we can do is to think about adding up all of these squared differences. When we do this, this produces the first measure of variability that we referred to before as the sum of squares. More completely, it's the sum, notice the sigma there, of squared differences, which we abbreviate as the sum of squares, or simply the SS. And what this gives us a measure of is the total variability in a data set. Because notice what we're doing. We're adding up. We're calculating a total variability. In other words, we're looking at what is the total distance of these different points from the mean. Now they're squared, so technically we're looking at what is the total squared distance. But conceptually, again, this is a measure of total variability in a data set. What is the total distance when we add them all up of the different points squared from the mean? This then is going to give us the basis for our other measures of variability as well. Because now that we have this total distance, we can again just try and figure out what an average is to get what we were looking for originally conceptually, the average distance of each point from the mean. So then the next step is to just divide by the number of scores that we have, or the number of terms that we have. In this case, we have 9 different scores, so dividing by 9 is indeed then going to give us the average squared distance of each score from the mean. This is exactly what we refer to as the variance, and this is the formula for the variance. Now in particular, this is a formula for the population variance, which we calculate using an n in the denominator. Now, as we mentioned at the very beginning of this lecture, there is a distinction between population and the sample, and in particular in terms of some of the formulas that we're going to come up with based on whether we're assuming that we're dealing with an entire population or a sample. Now this formula makes some sense because of the way that we're deriving it, but this is actually the formula for the population variance when we divide by n. Something that I'll mention here, and we need to remember this. Okay, we're not going to get into a lot of the details at this point about why this is the case, so I'm just going to ask you to take my word on it for now. Is that when we're dealing with a sample of scores, instead of an entire population of scores, we have to make a minor adjustment to this formula so that it becomes more mathematically correct. Okay? In particular, to come up with the sample variance, notice the change here in the notation from sigma squared to s squared, the symbol for the sample variance. What we then have to do is, instead of dividing by n, divide by n minus 1. Everything else stays the same, and the general logic stays the same, so I don't want you to get hung up on that difference between n and n minus 1. Just remember the following. If you're assuming that the set of scores on which you're calculating the variability is the entire population of scores that you could ever see, and in terms of what you're dealing with, then you can divide by n. If what you're dealing with is a sample of scores from some larger population, then what you're going to do to calculate the variance that we're going to be using is to divide, instead of by n, dividing by n minus 1. Now, given that distinction, what we have, again, so far, is whether we're dividing by n or n minus 1, an average now. But what is it an average of? It's an average of squared differences. So we're not quite back to what we were looking for in the very beginning of our variability discussion, the average distance of each point from the mean. What we have right now is the average squared distance of each point from the mean. And so when we report the value of the variance, those numbers are actually going to be a lot bigger than we think it is. In other words, because we've squared all these differences to get here, the value we get for the variance is going to be larger than the average distance of each score from the mean because we've squared them. What we need to do, in a sense, is to sort of conceptually undo that squaring operation we did earlier. Well, luckily in mathematics, when you take the square root of something, that has the effect of undoing squaring in the first place. And although it's not mathematically, technically going to completely undo it, conceptually I think that's the best way to think about what we're doing here. If we take the square root now, what we've done is to undo, essentially, conceptually, that squaring that we did in the first place to make all those values positive. So now this, which is referred to as the standard deviation, and the notation makes perfect sense because instead of s squared, now we're just looking at s. This now gives us the closest thing to what we were looking at from the onset, and that is the average distance of each point from the mean. And again, let's recap how we got here. We took the distance of each point from the mean to figure out how far it was. We then squared those values to make sure that positive and negative deviations, those scores above and below the mean, got treated the same and didn't cancel each other out to produce a sum of 0. Then we added them all up to get a total amount of variability. We divided by n, or n minus 1, in order to get a measure of average variability, the variance. And then, in order to sort of undo that squaring operation we did earlier, we're going to take the square root, and this isn't going to bring the value back down to the same scale of measurement that we were using in the first place. So instead of squared units or squared points or squared scores, now we're back dealing with our original units, our original scale units or scores. And then again, this being the formula for the sample standard deviation, there is a population standard deviation formula we can use, again, just by changing that n-1 back to an n. And it'll typically be clear in application whether or not we're dealing with an entire population or whether or not we're just dealing with a sample of scores. So it should always be clear in practice whether you're using n or n-1 in any given situation. Now, that actually concludes the second part of this lecture on descriptive statistics, covering the different measures of variability. Remember again what we introduced to summarize: a measure of range, which is a very crude measure that just tells us the distance between the highest and the smallest score in a data set. Now, that's not a very good measure to take every score into account to give us a comprehensive measure of variability, for which we looked at 3 different measures in particular. The sum of squares, a measure of total variability; the variance, which is a measure of average variability; and then the standard deviation, which is also a measure of average variability, but one that is rescaled back down to the types of scores that we had originally. And for each of those latter two, the variance and the standard deviation, we have both a population formula and a sample formula, depending on whether or not the set of scores we're dealing with is assumed to consist of the entire population or a sample drawn from that population. And all that does is to change the denominator slightly for the sample formula. And again, we'll encounter this a little bit later in the course and next semester as well, some of the rationale for that. We're not going to focus on that here. That concludes this lecture series, and you should now be well equipped to complete the quiz associated with this material on descriptive statistics, central tendency, and variability.